Ladies and gentlemen, today's class recording has started. So, I've made mention of this over the past couple of days, and so today we're going to start getting into it a little bit more. The idea that these concepts of electricity and magnetism are related to one another because they're basically caused by the same thing. And so, this all starts back in the 1780s? Yeah, or early 1800s. So here's a Danish scientist. His name is Hans Christian Ørsted. Not Hans Christian Andersen, the guy who writes fairy tales. You know, still heard of him before. So he is a scientist, and at the time, scientists, I don't want to make it cheapen the profession, but scientists were almost kind of like magicians. They would sort of go around and do shows and say, hey, look at this, woo, you know, like that kind of thing, while doing research and learning things. But sometimes that sort of demonstration would lead to some discoveries. And so while Ørsted is doing his demonstrations with electricity, he starts up a current in a wire, and he realizes that when he does that, the compasses that he has there are affected, right? And we kind of talked yesterday about the idea. Yesterday, it was Tuesday, I guess. So I put another hanging magnet up over here to make ourselves another compass, right? And this hanging magnet interacts with Earth's magnetic field so that the north pole of this magnet points towards the north pole of the Earth. But if some other magnetic field is stronger than the Earth's magnetic field, I can get that magnet to move, right? Yeah. This bar magnet, obviously not as big as the Earth, but because it's closer to that magnet, its magnetic field overpowers the Earth's magnetic field, and we can make it move, right? What Ørsted realizes is that when the current is flowing through a wire, it actually makes a magnetic field. There is no quote-unquote magnet there, but there is still a magnetic field because it affects other magnetic things. And so we can get a magnetic field through an electric current. Okay? So, I can't remember if I included this in your outline or not. So, I didn't. I forgot. I changed this presentation a little bit, but I forgot to include some things in the outline. So, just for some background. We are going to basically be looking at, over the next couple of days, this idea of electromagnetism. This combination of electricity and magnetism that makes up the electromagnetic force. The electromagnetic force comes from the interaction of electric charges, positive charges and negative charges. We explored those in our last unit on electricity. When those electric charges are stationary, we talk about electric forces, and that's when we talk about like the balloon moving somebody's hair, or when we talk about rubbing the PVC pipe with the felt, and you can get the little pieces of paper to stick to it, and all that kind of fun stuff. There we're talking about stationary charges. When we talk about moving charges, like in the magnetic domains that we talked about on Tuesday, that's when we start getting to magnetism. But it still all comes back to electric charges and the forces that exist between them. Whether they're stationary or whether they're moving, we call it something different, but in a lot of ways it's the same exact thing. And that's why it's the electromagnetic force. So, let's talk about that electromagnetic force. Okay? So, a magnetic field, quote unquote, circulates around a wire that is carrying current. So first, a wire that's carrying current means what's happening in it. The electrons are moving. Those charges are moving through that wire. We kind of talked about the idea that they can kind of flow from one atom to the next because they're not held really tightly, et cetera, et cetera, et cetera. If we find that the magnetic field lines are concentric circles around the wire. Do we understand the concept of a concentric circle?
No.
Or two concentric circles? Two concentric circles are circles that have the same center point, but a different radius. Does that make sense?
Yeah.
Alright? So the center point of the two circles is exactly the same, but they have a different radius, so they're bigger. One's inside the other one, right? We could have multiple concentric circles if we need to. So we find that the field surrounding this wire is a bunch of concentric circles. Stronger, closer to the wire, weaker as we get farther and farther out. Okay? And we can show that by placing a bunch of compasses around this wire, and those compasses are affected by the magnetic field produced by the current. Normally, all the compasses point exactly the same way. They point north. But when we put them around a wire that is carrying current, and you can see here in this picture, right, there's a wire that comes through here, and there's an arrow that's labeled I, and we know that I represents what? From the last part of our unit, current.
Oh,
What represents voltage? What letter do V? V probably, yes. Okay. So, when we have current flowing through this wire, these compasses no longer all point towards the North Pole. They are affected by the magnetic field that is produced by this wire, that is, as it carries current. Okay? Good there? All right. So, how does the field look? So, we get to make hand signals now. Okay? When we look at the field that is produced by a wire that is carrying current, we use what we refer to as the right-hand rule. Okay? Hold on 1 second. All right. So here is a conductor. Okay? It's a rather large conductor, but it's a conductor. I'm not going to hook it up to a voltage source. I'm just going to use it to demonstrate. Okay? So, when current is flowing through this conductor, we use our right hand and we put our thumb in the direction that the current is flowing through this conductor. Okay? Now, here's the trick. Back before we understood what charges were, back before we understood that charges were actually parts of an atom, the positive proton and negative electron, we defined the flow of current as the direction that positive charges flow. Okay? We now know that really it's negative charges that are much easier to move. So this idea of positive charge flow we refer to as conventional current. Okay? Little confusing, I know, and that won't necessarily come up on the test, but when we're using the right-hand rule, we talk about the flow of conventional current. So if electrons are flowing from your right to your left, conventional current flows from left to right. Okay, I know that's confusing, but we set up these ideas before we really understood them, and so we kind of kept them moving forward. The biggest thing being, though, if we take our thumb on our right hand, putting it in the flow of conventional current, and then you take your fingers and you curl it, those represent the circles of the magnetic field that surround the wire. Those are the field lines, and they would point in that direction. Okay? If we flipped the battery, you guys saw this in your lab the other day, if we flip the battery around and cause the current to flow in the other direction, now the field lines point in the other direction. Here, right, up at the top, the field lines point out towards you. Does that make sense, right? You can see the tips of my fingers, okay? But if we flip the current around, now above the wire, the field lines point towards me, right? They point in the other direction. So the direction in which current flows affects what kind of a magnetic field is produced around this wire. So, to find the direction of the magnetic field produced by a current, point the thumb of the right hand in the direction of the conventional current. Okay? And then, which is different than the direction that electrons actually flow. And the fingers then curl in the direction of the magnetic field. Okay? Am I missing a line there? No. Just kind of a short line. Okay. And then the way the fingers curl, that gives us the direction in which the magnetic field, right? Their magnetic field is always circles that surround that wire. It's just a matter of which way do those circles point. Are they clockwise or are they counterclockwise? Good there? We okay with that?
Yeah.
All right.
Sure.
That's great. Okay. When we talk about how strong of a magnetic field is produced by this current, or when we talk about how strong of a magnetic field is produced by a current flowing through a wire, we talk about two things. The magnetic field is directly proportional to the current, okay, and inversely proportional to the distance from the wire. So the more current we have flowing through our wire, the stronger magnetic field it produces. But also, depending on how far away we are, that can affect it as well. Okay, go ahead.
What is number 1 on the
Oh, right-hand rule. Roman numeral 1, letter D, number 1. We call this the right-hand rule. Because you got to use your right hand in order to do it. Now, if we were talking about electrons, we would use the left hand, but that's not how we do it. So. And how strong of a magnetic field depends on two things. It depends on how much current we're flowing, and it also depends on how far away we are from that wire. Okay? Good there? All right, here's the thing. So we have a wire that's straight, but we can take that wire and we turn it into a loop like this. Okay? Okay? Now we have a loop of wire. When the wire flows straight from one side to the other, because we have a loop of them, right-hand rule, right? The fingers point this way, the magnetic field goes around that way. Good? Okay, right? But let's say we take this and not necessarily connecting it to itself, but connecting it to the two sides of the battery, but now that wire is in a loop, right? If we look at the right-hand rule in different parts, regardless of where we are on this loop, my fingers always point through the middle towards the board. Does that make sense? Okay. What happens then is that when we make these field lines on a loop, your fingers always point the same way. And so now the field from the top of the wire and the field from the bottom of the wire start lining up with each other. Okay? And I think you have these pictures actually at the top of the back page of your outline because I couldn't fit them on the front. Okay? But now we have all these field lines pointing in the same direction. If you remember from Tuesday, this setup of field lines is exactly the same as the field lines that surround a bar magnet. Out of the north into the south. Out of the north into the south. So when we take this wire and we have the field that sort of surrounds it, but when we turn it into a loop, now this wire behaves almost exactly the same as a bar magnet. Okay. So one side of our loop behaves like, okay? So when the wire is bent into a loop, the field lines produced by the current all point in the same direction, or through the middle of the loop.
Or what?
Through the middle of that loop. And this makes our loop of wire behave just like it was a bar magnet, where one side of it acts like the north pole of a magnet, and one side of it acts like the south pole of a magnet. Right? You can see from the picture, there is no magnet actually there. It's kind of like a ghostly image, but that's what it behaves like. One side of the loop behaves like the north magnetic pole, one side of the loop behaves like the south magnetic pole. Good with that so far? Okay. When we have two loops, each with their own current, now it's almost like we have two bar magnets. Right? These loops would attract each other. North pole, south pole. Right? But more importantly to our discussion, having two magnets is better or stronger field than having only one magnet. So now if we have two loops where the current is flowing in the same direction, we get a stronger magnetic field. The more loops we have, the stronger the magnetic field is. Right? And this leads us to a discussion about electromagnets. Okay? Over here on the table, this is something that we call a solenoid. It's just a wire that has been wrapped around this wooden, or I guess plastic, this plastic, whatever this is, spool, I guess, right? It's like a spool of thread. Right? So Frank, can you see that the wire is attached to this here, and then it's attached to this over here? Okay, so it's just a coil of wire that's wrapped around this spool. Okay? And if I attach, right, one side of the battery to one side of the spool, and the other side of the battery to the other side of the spool, right? Current flows through that wire, the light bulb lights up just like we did before. Okay? But now all of these wires are producing a magnetic field. That coil, right? We said when we turn our wire into a loop, it acts like a bar magnet, right? One side north, one side south. This is, I don't know how many turns are in this coil, but a bunch of small little bar magnets. And so now the little magnetic field of all of those little coils acting like bar magnet ends up lining up together. And I can take this, let's see if it works. Right? And I can move the wire, and I can move the magnet. Right? Because of the magnetic field that is being created by current flowing through here. Okay? Jack, go ahead.
So is one of the sides of that, whatever it is, on the north and south?
So, here, right? Correct answer? Yeah. Or short answer? Yes. Right? So here, this is attracting, right? So if I take this, I just slow it down a little bit, but now it's repelling, right? Yeah. So yeah, it behaves exactly like a bar magnet does. You got two sides, one acts like north pole, one acts like south pole, right? So that coil of wire we call a solenoid. The solenoid is just the coil of wire. But when we have current passing through it, all of the loops behaving like one small little bar magnet end up now behaving like one big bar magnet. But it's only magnetic when what happens? When does the magnetic field exist? Only if what's happening in our solenoid. Only if current is flowing, right? And that's why we refer to it as an electromagnet. Because it only exists, the magnetic field only exists when current is flowing, right? So, another example, right? Here, this is just a metal rod, okay? This is a paper clip, right? This is not a magnet. we said that some materials, when we put them, some materials, when we put them in a magnetic field, become magnetic within that field. Does that sound familiar from our discussion on Tuesday, right? So here, now because there's current flowing through this wire, it's behaving like a magnet, and it causes that metal rod to behave like a magnet, and it works right. Oh, get it to stick off of the tool. Oh, come on. Alright, so magnetic field isn't quite strong enough here, so what can I do to increase my magnetic field?
Add more loops. Add more
How do I add more
oil.
current? I can add more loops.
More batteries.
So, let's add battery number 4 in here. I'm probably going to blow out this light bulb. Actually, you know what I'll do? I'll just take out the light bulb. Do you guys trust me that do you trust me that the current is flowing through it? Yeah.
No.
So,
That's one of the different.
no, you're a hater, that's what it is.
I am a hater.
Keep questioning things, Chris.
I always question.
Alright, so, I attach this here.
Oh.
Oh, yeah.
Oh, man.
That's a lot stronger current because it doesn't have light bulb in it, so it's slowing down, right? So if I just connect this, you can see that. Can you guys see that it like makes the paper clip smooth on the table?
Alright.
If you want to come closer to see,
Oh,
come
come
closer.
closer.
Just make sure that you know. Come see back this way. So, alright, ready?
Yeah.
Oh. Yeah, I can hear you.
If you read it.
I heard you. There we go. Alright. But, what do I have? Can you see it? But, if I disconnect the wire, what happens?
No more.
Oh. So, that's still magnetic because it was magnetic, right? Okay. But, if I disconnect them, right, doesn't pick anything up. What? It only works when current is flowing through it, though. Okay? Alright, good. We okay with electromagnets? Let's call it a day. We'll pick it up from there on Monday, alright?